Hey, math people. We're looking at lecture one of we're going to call it Analytical Applications of Differentiation chapter. We'll do another chapter called Contextual Applications of Differentiation. So this one's more like the mathy stuff. And then when we get to contextual, that'll be more like the real life stuff. So for the next 6 lectures, it'll be pretty mathy. Remember to use the timestamps. This video is for you, Ashley. So yeah, whatever your name is, right? So make this video useful for you. The breakdown is we're going to start with the warm-up. We're going to build some intuition behind the mean value theorem. We'll define it. We'll see like what I call like AP official language if you're taking the AP calculus exam. And then we'll look at examples. So if you just need that, skip to there. We'll look at a table. We'll look to see when you can apply it, when you can't. That'll be the day. Okay, so warm up. Let me know what you think. Where are the functions? Where'd they go? Okay, where are functions considered non-differentiable? There's 4 major moments. 3, 2, 1. These are the major moments. So if we have a corner, right, the idea is you need local linearity, right? That's the whole point. And you need it to be non-vertical. Whoa, ZX. So if I were to zoom in to this point infinitely and forever, it always looks like a corner. But if I had something curvy, like x to the 3rd, you can see here that, well, if I were to zoom in at any location, like right here, if I zoom in enough, it looks like a line. So you need local linearity, and you also need it to not be a vertical slope. So that's going to be a corner. That's no good. Cusp, you have a infinite slope coming in from the left and right. Vertical tangent, that's an infinite slope. And then if it simply doesn't exist. So at 0 for 1 over x, we don't exist. You can't do that. You can't plug it in. If it doesn't exist, then you can't differentiate it. Okay, looking at the little warm up here. So mean value theorem is a nice thing you can do with access to the derivative. Before we define it, how about we just throw back to secant lines and tangent lines real fast. I want you to, right now, draw a secant line connecting the dots. So you can see there's a point here and there's a point here. What would that look like? And then thereafter, draw the tangent line that has the same slope as the secant line. So if we were to look at the first one together, and then maybe I'll just leave the second one totally for you. Of course, the secant line would just be this line connecting the slope, connecting the 2 points here with a slope of 1, it looks like. Up 1, right 1, up 1, right 1, up 1, right 1. So if I were to try to figure out where that is on the parabola, I don't know. It's like here-ish, probably. Let's go take a look at that. So get your answer for the second one in 3, 2, 1. Okay. Yeah, like here-ish, right? I don't know where that is. We can talk about that later. But the idea is, for mean value theorem, there may exist some point, if we have this thing called differentiability, there may exist a point within the interval where your slope is the same as the average rate of change. So that's our objective today, is to figure out when that occurs, right? Rather than saying like, oh, it's here-ish, or oh, it's here-ish, right? When does the tangent line have the same slope as the secant line? In a more rigorous, like literal setting. What we're doing here is we're setting the average rate of change equal to the instantaneous rate of change, i.e. the slope of the secant line to the slope of the tangent line. We know the expression for average rate of change. It's just change of y over change of x. And we know the expression for instantaneous rate of change. It's just the derivative. So I got to look for this value. If I know the parabola is this negative x squared plus 4x plus 1, is there some way, there is, for me to utilize these two expressions here to figure out what my c value might be? So on the left side, I want you to try this. On the left side, you're going to find an average rate of change from 0 to 3. And then on the right side, you're just taking the derivative. Okay? So I'm going to give you maybe 3 seconds here. You're finding the average rate of change, the slope, and you're setting that equal to the derivative, the instantaneous rate of change. 3, 2, 1, bam. Is that what you got? Right, we already knew the average rate of change was 1. We just kind of eyeballed it. I said up 1, right 1, up 1, right 1, up 1, right 1. That's 1. And then in terms of that instantaneous rate of change, it's just a parabola. We just use power rule twice over, set this equal to each other. That's a 2-step. We get 3.5. So you can see, yeah, it made sense. It was somewhere in between 1 and 2. It's exactly in between 1 and 2. It's at 3.5. 3.5. 3 halves. Those are different things. 3 halves. All right. Looking at the exponential, you can do that one on your own. Okay. Well, you don't know the equation of it, but we're going to unpack this more broadly. But there's a problem. What if these things happen? We talked about them. Corner, cusp, vertical, tangent, discontinuity. What if these things happen? Does this kind of break this average rate of change is equal to instantaneous rate of change idea? Well, I mean, try out the first one right away. If you were to draw the average rate of change slope, connecting the 2 points, that would just be the secant line with the slope of 0. Do we ever attain a slope of 0 on this cusp? No. I don't know. I don't know if I should have done 3, 2, 1. No is the answer. Because of this cusp, we didn't have this guarantee that there is a location in the interval where the instantaneous rate of change is equal to the average rate of change. And then here we see a non-differentiability. We see a discontinuity largely. It's a jump, and it's the same line of logic. This one's a little goofy though. If you just look at the same exact interval, but you just nudge it to the right a little bit more, that slope is up 1, right 3, and that actually kind of sort of happens here-ish. So sometimes this still works. Just because you have that non-differentiability doesn't indicate that you can't set the have the average rate of change equal to the instantaneous rate of change. There's the word. But it doesn't give us that guarantee. So we lose the guarantee, but it can sort of still kind of happen. Okay, so here it is. Mean value theorem is what this phenomena is called. If f of x is continuous on the closed interval and differentiable on the open interval, then there must exist some c where that derivative is equal to the average rate of change. This is the guarantee. You get this for free so long as you have continuous on closed and differentiable on open function. You get it for free. All right, so we're going to be looking at this parabola. I'm going to practice the official language. What you can do if you want to practice this one is just do the thing. Well, first we should verify that the criteria are met. Is this in fact a function that's continuous on its closed interval and differentiable on its open? So we're looking at the interval from -7 to -2. Looks good to go. It's a polynomial. So if we saw a jump, if we saw a cusp, if we saw a corner, then we don't get the guarantee. Okay, so we get it here. This function is continuous and differentiable from -7 to -2. Connected the whole time, no corner, cusp, vertical tangent. All right, so yeah, if you want to go ahead, take the derivative here and set it equal to the slope connecting these 2 points, the average rate of change. See if you can do that on your own. I'll provide you the official language that the AP gods may ask of you. Consider yourself lucky if you're in a Calc 1 course at university. All right, 3, 2, 1. So if you're taking the AP exam and you need to justify mean value theorem, you're going to say something along the lines of, okay, well, f of x is a polynomial, so we're good to go. And it is known to be continuous on the closed bracket, -7, -2. And differentiable on the open, -7, -2. This just means therefore, ... You don't even need it. It's a fancy flex. Mean value theorem can be applied. Yeah, okay, so average rate of change, I went ahead and computed to be -1. Instantaneous rate of change, I'm loving those quadratics because that's just a power rule, 3 times over. Went ahead and set that -1 equal to it, and it turns out somewhere at -9/2. So that's 4.5-ish, which is somewhere over here. We have the, average rate of change slope in blue, the same as the instantaneous rate of change slope in green. Okay, so let's roll through some examples, yeah? So you do this how you want to do this. If you want to just wait for answers, that's a tactic. But what I recommend is to try them on your own. You're taking the derivative and you're setting it equal to that derivative expression. What were to happen if you found the average rate of change here? So that's plugging in 0, getting a number, plugging in 2, getting a number, and then taking that difference, so those are your y values, over the difference in your x values, which is just going to be over 2. So give this one a go. Yeah? 3, 2, 1. Went ahead and did that. So I mentioned, okay, you plug in 0, you plug in 2, find that difference. Okay, so it's like negative 1/3, I guess. And then that's going to be over the difference of the x values. So remember, this is literally just slope. If you ever get bogged down in all the crazy equations that you got to know, I always like to advertise to just take a step back, strip the layers. This is literally Algebra 1 slope. You know, does that make it easy? No. Simple, but not easy. All right, anyway, we got negative 1/6. I went ahead and took the derivative. Unfortunately, I had to use the quotient rule, which sucks. So I had to set this monstrosity equal to negative 1/6. I did some cross multiply action. I combined like terms onto the right side because I just saw more negative coefficient here on the left. So I just scooted everything onto the right. I said, great, let's factor. And then I thought, shoot, this can't be factored. So I had to use the quadratic formula. We're starting off with the hard one. Sorry about that. We'll do some lighter ones after this. We'll go back to polynomials. But you get two solutions here. You get negative 1 plus root 3 and negative 1 minus root 3. Issue is the interval is from 0 to 2. So, I mean, this is definitely outside the interval. This is negative. Root 3 is like 1.7. So, I mean, think about it, right? It's just below root 4, which is 2. So this is like 1.7-ish. So this is like 0.7. That's within the interval. This is the only solution that works. The other one is outside the interval. You can have multiple moments within the curve, right? We can just like, can I draw it? Can I draw it? Can I draw it? Can I draw it? Yeah, I'll draw it. Hopefully you're fine with this. I mean, think about it, right? If you have a slope here, you know, wow, that's big. But actually, that works out pretty nice. Look, if you have a slope here, that the average slope is whatever this, say, blue line is. So we'll just say this is like 1-ish, right? We actually attain this slope 1, probably somewhere over here, right? 2, like here-ish, 3, 4 times. So you can have multiple moments, but they need to be contained within the interval. Okay, before we move on to the next one, just want to highlight the fact that you really do need to check to see that your function's continuous and differentiable on the interval first. This one happened to have been so. If you look for continuity issues, what can I not plug in? I can't plug in the negative, what is that? Negative something. If I were to set 4x plus 4 equal to 0, negative 1, there it is. We have an asymptote at negative 1 here. I'll even show it. But that's outside the interval. So having a general moment of, discontinuity is fine so long as it's outside of the interval. There you go. Yeah, so we see here the asymptote lies on negative 1. Everywhere else is good to go, though. And you should also see when it's non-differentiable. That's like what numbers can I not plug into the derivative? Again, it's just that negative 1. Right? Plug in negative 1 to the denominator, you get 0 for each of those. So always check for that first. So as we look for the next one, which we're going to start, okay, nice, pretty cubic. This is the one. Find the average rate of change. Set it equal to the derivative, but after you first check to see it's continuous and differentiable on that interval. So 3, 2, 1. Here it is. Okay, it's a polynomial. We're fine. No issues with either the function or the derivative. You take the average rate of change. It comes out to good old 1. And then we're setting the derivative, which is a quadratic, because that is the derivative of a cubic. We're just solving this out. So setting this up, we're looking at another quadratic formula, rough but doable. And we get two solutions. We get a positive and negative. Now we have to make sure it's in this interval from negative 1 to 3. We would say, well, root 13, shoot, what is root 13? It's just under 4, all right, because root 16 is 4. So this is like 3 point something. So we got like 7 point something over 3. That's lower than 3. So we're within the interval. And if this is 3 point something, this is 4. So this is like point something. This is close to 0. So having that number sense numeracy can go a long way. Of course, if you had a calculator, you can just sit there and be like, all right, are we good to go? Are we good to go? Yeah, we're good to go. Yeah, we're good to go. Okay, next one, another cubic. Give it a go. 3, 2, 1. All right, yeah, good to go with continuity differentiability. It's a polynomial. Average rate of change is 0. That's a happy coincidence. It's easy to solve when you set expressions equal to 0. By the way, if you ever heard something called Rolle's theorem, it's just when you're kind of finding mean value theorem specifically when the slope is 0. So this is just a special little case. So we're taking that instantaneous rate of change. We're getting this quadratic. We're setting the quadratic equal to 0, and we're getting a nice factor. The problem is that 2 exists, quote, outside the interval. And you may be thinking, what? 2 is on the interval? That was a little mean. But let's throw it back to the definition here. Then there must exist some c where f prime of c is equal to the average rate of change on the open interval. This was a happy coincidence, this 2 existing on the endpoint here. You get the guarantee on the inside, but not on the outside. So this was a little gotcha. I wouldn't do this to someone on a test or quiz, but I don't know, it's fun just in the context of this scenario. Make sure it's within the open interval. All right, last one. 3, 2, 1. Okay, looking good. We're looking at just a basic square root, which is not an issue so long as the inputs are all positive. And not all positive. The outputs are all positive, which they are. Because if you plug in -4, that's 0. That's the left endpoint. And then if you plug in any other number, -3, that's a positive number. -2.5, that's a positive number. That's going to shoot out, so we're good to go. Can't have negatives underneath the radical. All right, something kind of fun here too is that this is technically not differentiable on the closed interval. The derivative at exactly -4. Ooh, what? The derivative at exactly -4 is infinity. It's a vertical slope. However, we don't care about that. All right, there's that vertical. We don't care about that. And the reason why is we need differentiability on the open interval. So why am I being a little gotcha on some of these here? Because I don't know how your teacher's going to be. This is a little overkill, maybe, for some of the nuances. Anyway, we're good to go, though. Differential on that open. Go ahead, take that average rate of change. You get root 2 over 2. When you take that derivative, this is our expression. Some cross multiply action, you get -7 over 2. All right, table time. So with these tables, we would need to just use what we have access to. I like to think about these table values as like snapshot moments of your overall function curve journey. The point being is that I don't know what happens in between them. So if I were to plot these ordered pairs, right, and I think I could do it on a table, 0, 1, 2, 3, and then we got 4, 5, 8, 13. You know, we can't really make any assumptions here. Like, it looks like it could be exponential, but who's to say? Who's to say? This graph doesn't have other plans, and it does something like this, what my cursor is doing, and it's just going up and down in between. Maybe it goes all the way up and then comes back down, or maybe it goes all the way down and comes back up, or maybe it's just line, line, line. We don't know. We just have these snapshots. Okay, so see which of the following must be true. Yeah, I'm going to just let it rip. 3, 2, 1. Okay, so let's talk about each of these. So if you're thinking, okay, well, in between 0 and 3, the slope's got to be 3. Because if I find that average rate of change, I do my change in y. I do my change in y over change in x. And you're thinking, oh, it's got to be, right? It's got to be. We don't know that, right? We don't know that at exactly 1.5. We know nothing about what happens at exactly 1.5. So I can't make any specific claim about its slope at 1.5. Not necessarily. Could be true, could be false. Okay, is there some value, so some C1 value, any number, where the derivative is equal to 3? Yes, this is guaranteed because we know that it's continuous on 0 to 3 brackets, and then so open or closed, and then differentiable on the open interval 0, 3. So yeah, this is just good to go. The average rate of change is 3, so somewhere, don't know where, you're guaranteed to have a slope of 3. Are we guaranteed to have a slope of 1.5? This one was very mean, because if you find the average rate of change from 0 to 1, this slope is 1 right here. And then what else did I do? I did from 2 to 1. And then this slope is whatever that is, 5. Right? No, it's 3. Yeah, okay, it is 5. This slope is 5, and this argument would be fine, but I found the slope from 1 to 2. So this slope right here is 3, and this slope right here is 1. So if there's an old friend that you haven't called up lately, you might be thinking of the intermediate value theorem. What you could say is, well, I know at some point there was a slope of 1, and I know that at some point there was a slope of 3, so since it's continuous, I must have had a slope of 1.5 at some point. This was a little extra. And then, well, can we kind of extend that further? Have we experienced a moment, can we guarantee a moment where we have a slope of 6? Not necessarily. There's no like little sub interval here, like from 0 to 1 or from like 1 to 3, where the slope is larger than 6. I think the biggest is right here with the slope of 5. So not necessarily. If this were to connect, you know, just in kind of the way you would expect it to, it would not have a slope of 6. However, if it did its own thing, and it just spiked really high up and then really low down, then it could potentially have had a slope of 6. Okay, all right, last little section. We just gotta determine if we can apply it, yes or no. So we're gonna do this as a power round, all right, just at the end here. Are we good to use it, yes or no? All right, just scan your way through. 3, 2, 1, last round. Here are the scenarios here. We are not continuous at 0, which is contained in the interval. No good for the first one. For the second one, you know, it looks like there might be an issue, and that number is 2. You can't plug in 2. 2 is fine, though. It doesn't exist within the interval. We're good to go. Here, this is how we create a cusp. So, all right, let's think about that. If we have a cusp at exactly -6, that's totally fine. And the reason why is that it's an endpoint. If it happened inside the interval, that's a problem. Here we have a corner from the absolute values, and it's going to happen at 2, which happens in the interval, and that's no good, so MVT cannot be applied. The cube root, this is going to create a vertical tangent. And by the way, if you're just like, what? How does he know those things? I don't blame you. You just play around with like powers of x to see kind of what you get. The ones I ask the kids to kind of know is you have like this even over odd, you'll get a cusp. And then here you see the cube root. If you have odd over odd here, you get the vertical tangent. Hopefully you're on board with me saying this has a corner. But if you're kind of like a little, that's where the like we hope you know function stuff comes into play. Anyway, you get a vertical tangent here at 4. You set this equal to 0, and that's contained in the interval, so no good. And then lastly, tangent. If you remember the interval of the waves of tangent, it's from -π/2 to π/2. So this is good to go. This interval's just fine. If it extended further to like pi or something like that, then that would be an issue. Okay, that's it. I'm gonna go. Math on.